Hello, everyone, and welcome to today's exciting webinar. I'm Tim Stark, and a professor of civil engineering at the University of Illinois and the technical director of the Fabricated Geomembrane Institute. This is our fourth webinar of 2023, and we have 8 more planned for 2023 with great speakers and timely topics. I'll show you the next webinar speaker and information on the last slide today. During today's webinar, we welcome questions and comments which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our distinguished speaker will address them at the end of today's presentations. Viewers attending the Japan, Australia, and South Africa time zone presentations, please submit your questions during the presentation or the follow-up survey that you will receive after the presentation. And the speaker will address your questions during the follow-up podcast that we'll have. A PDF of the slides is already available in the handout section for you to download and follow along during the webinar. A recording of this webinar and the PDF of the slides will be made available on the FGI website after today's presentation. The PDA certificates will be sent automatically to all who attend the entire webinar. Okay. Today's webinar I'm really excited about. This is the second part of a 2-part webinar, and just really excited that Professor Jorge Zornberg is going to give part 2. Jorge and I were involved in an interesting case about the cause of damage to a geomembrane installed in what I'll call an impaired water pond for an oil and gas development site. If you missed it, last month I gave the first perspective, or one perspective, of the case and the performance of the geomembrane. And today, Jorge Zornberg will give a second perspective on the project. Through these 2 webinars, we think the listeners will learn a lot about potential problems that can develop, and most importantly, recommendations for avoiding a similar expensive and problematic situation. So today, Jorge Zornberg will present his analysis, and Jorge Zornberg is a distinguished professor of civil engineering at the University of Texas at Austin and a leader in the geosynthetics industry. He is also past president of the International Geosynthetic Society and was honored with the Zornberg Lecture by the IGS. So the formal title of today's webinar is Geomembrane Damage During Oil and Gas Operations, Part 2. So Jorge, thanks so much for squeezing this webinar into your busy schedule and joining us from Austin, Texas. We look forward to your perspective on this important case. So please, you've got controls.
Very good. Can you hear me well?
Perfectly. Yep.
Perfect. Well, thank you, team, for the introduction, and thank you so much, because you're not only an organizer of this, but you're also a kind of co-presenter. So this is just for the audience to know, an easy path for Tim and I to present this case could have been to find a common ground and to present only what are the aspects in this case that are a common ground. But it requires a lot of trust, a lot of respect, to do what Tim and I are doing right now, which is we're going to deal with the aspects in which we have a common ground, and there are many, but also the different perspectives at the time of a litigation. So I think that this is a great way to learn, and I thank you, Tim, really for making this happen. So let me walk you through this. Geomembrane damage during oil and gas operations, part 2. So as you may have heard from Tim before, or from your experience with the oil and gas industry, ponds are very much required. Lined ponds are very much required during fracking operations, for example. In this case, we have a view of a lined pond in which we have liquids, actually impaired liquids, and these are a combination of water. These are the liquid that is going to be introduced as part of the fracking operation includes proppant, typically sands. It includes chemicals such as surfactants and other type of chemicals. And then it's a flow back that comes back, and it comes with heavy metals. It comes with the flow back that comes back has a lot to do with the actual formation where this is taking place. This is not the site under discussion, but it's an illustration of a site where you can, of a pond that is typical of the ones that we're going to be talking about. As part of this ponds operations, as part of the flow back, as part of the collection of the liquids, there is a lot of hoses, a lot of operations coming in and out. And here we have a view of such operations. And here we have another view of typical operations of essentially hoses encroaching into the surface of the lining system. But the site that we are going to be talking about is a different one. And let me go very quickly. If you have not heard Tim's presentation, part one, last month, please go through it. But I'm going to give you in one slide a lot of the information that Tim covered in more detail. So essentially, we're talking about an oil production company that sued a liquid treatment operator. And this was because potential inadequate services that may have caused holes in a pond geomembrane liner. Now, this was at the time after the fluids had escaped, and this had adversely impacted groundwater and the soil surrounding. And then the allegation was, and Tim explained this in detail, was that the hoses that were used during the water treatment, the liquid treatment operations, had caused the geomembrane holes. Now, the holes were connected. These were kind of, give or take, 20 feet long segments that were connected to each other with steel cam locks, and they have been reported to be wrapped when in operation, but these were a lot of the focus of potential damage that they may have caused to the facility, to the liner. Thick sediment layer was encountered during pond dewatering, and during this dewatering, shovels and high pressure washing was reportedly causing additional damage. And however, after the sediment was removed, several hundreds of holes were discovered. So we're not talking about a few holes, we're talking about hundreds of holes. I'm going to get into the detail of a survey of such holes that ended up identifying over 400 holes in a comparatively small area. Now, however, after removal of the geomembrane liner, and there was an underlying geotextile, it was also discovered that in the underlying subgrade, there were a significant number of shards or rocks. And they were also concentrated in the area where the main damage had occurred, which was in a specific area within the lined pond. So Professor Stark, in his part one of the presentation, focused on one of the potential causes of these holes. Specifically, he focused on the potential damage caused by steel cam locks as the primary cause of the geomembrane defects. In my presentation, this part two will now focus on the presence of rocks on the underlying geomembrane liner and their potential for having been the primary cause of the geomembrane defects. So before I showed you some generic ponds, this is the pond under discussion. And here you have it on the left, and here you have, here to your right where my pointer is the north, is pointing north. This is the north side of the pond. And an important aspect that I'm gonna point are these, we're gonna go over the lining, the layout of the different players at the time of the operations that took place during water treatment. And here you see 22 poles, 22 reference poles that I'm in pictures that I'm going to show you of the slide of the site. I'm going to be showing these different poles as a reference, and this will play an important role during the analysis that I'm going to present. So in this agenda, I just went over a recap. And I'm gonna now get started with Tim presented the background on this side. I'm gonna present some complementary background, specifically some complementary information, some different twists on several aspects, specifically on the sequence of events, on the pond liner configuration and materials, water treatment operations, how they were conducted, and the presence of rocks as they were identifying in the subgrade underlying the liner. Now, later I will talk about the different causes and the potential causes of the geomembrane defects. And again, it's a second perspective to the one that Tim has presented. And then we're gonna wrap up with some conclusions on recommendations. So let me get into some complementary background. So the sequence of events started with over a decade ago, the liner was installed. And then another important landmark was essentially monitoring wells were installed in March 2012. And soon after that, liquid treatment operations that are the operations in being disputed took place, give or take a month after monitoring had been initiated. But then a series of events took place. Essentially, there was an inspection that was conducted right after the liquid treatment operations and no issues were found. But soon after that, groundwater samples started indicating high conductivity. So a potentially logic aspect to consider was, well, maybe this is related to the liquid treatment operations. So that's a valid concern, even though monitoring had started recently to begin with. Additional holes were discovered. There were water transfer operations, and during these water transfer operations, even after the high conductivity had been identified, were discovered. These were caused by a different operator. SIPs were discovered, and then the decision was, because there were fines and there were significant costs, to essentially to lower the water level, and an accelerated fracking schedule was initiated to lower the liquids. And then it was in June, again, we're talking about April liquid treatment, June, pressure washing started on the liner, started being conducted after having drawn down the water level, and here's when the hundreds of holes were discovered. However, after having discovered the holes, the evaluation continued, and around September is when essentially the geomembrane liners were removed, the geotextile underlying was removed, and then is when significant number of comparatively large rocks were identified immediately below the liner. And a couple of years later is when this litigation started. So this is the actual timeline, just for you to keep this in mind. But let me bring you back to this one aspect, the 2012, the June 2012 pressure washing operations. And this is essentially, these are pictures taken during those operations, again, after the liquid treatment and the litigation had taken place. And here you see a comparatively thick, reportedly, it was not uniform throughout the entire pond, but reportedly a foot thick at some locations of sediments, these black sediments, and they started being removed using shovels, and they were cleaned up in order to expose the surface using pressure washing. And Tim got into how this was probably not a good idea. Additional damages were reported as part of these operations. I'm going to show you a picture that was taken at the time of these high pressure operations and shoveling on the liners, and these are the type of defects that were identified once the cleaning was taking place at a specific location that I'm going to discuss. It was on the north side. The specific location was on the north side of the pond, close to the northeast corner. So these are typical defects, and I'm going to get more into the details of the actual defects that we're going to see later on as being typical typical of the type of defects that were found. What is not typical are these scratches. A very robust survey was conducted, and these scratches were not identified, potentially these being now scratches that are not representative of what happened during water treatment operations, but potentially maybe even surficial scratches that took place during water cleaning operations after the dewatering and the washing of high pressure washing of the surface of the liner. But this is a view of the zone, and I mentioned that most of the defects were concentrated in a specific location. This is the northeast corner. This is the north side of the pond, and there was a significant concentration of defects towards the toe of the side slope. This is a 3-to-1 side slope, and at the bottom, nearby there, it's not exactly at the corner, and this is going to be an important aspect of this discussion, is beyond this is the east side slope, is beyond the toe of the side slope, of the east side slope, but I would say close to the center, but more somewhere between the center and the corner of along the north side of the pond liner. This is a bigger, this is a panoramic view of the site. Again, we're going to discuss, and that's why I'm going to particularly focus on the actual layout of the hoses and of the treatment, because taking pictures in perspective may be deceiving. So here you see the full site, and this is the northeast corner where the operations were initiated, and this is where the locations of highly concentrated number of defects occurred. Here is below a Google Earth maps, and we're going to see that this is particularly relevant in the upcoming evaluation that I'm going to show you. And again, in these Google Earth maps, and this is the north slope, the north border, and here you see the 22 pole fences, poles of the fence that are going to be used as a reference. Okay, this was this Google Earth map was reported to be in May 2013. You can see here an access road that had been constructed to gain access to the facility. All right, but so that was the timeline, an important aspect of the timeline. Let me take you back to the point liner configuration, because this is the time when we go back to how was this constructed, how was this designed, and what we found was that this was not the most or the better documented type of site. Indeed, these are the drawings. This comes directly from the drawings at the site. And I'm going to call your attention to this particular facility was originally designed as a freshwater impoundment, not as an impaired water impoundment, which ended up being how this facility ended up being used. Indeed, when we look at the drawings used for this particular facility, this is a very simple liner, very different than the one that ended up being constructed. Is actually reportedly, according to the drawings, a 30 mil HDPE liner, geomembrane, and we're going to see that this is not how ended up being constructed. So the pond was originally designed for storage of fresh water, not of impaired water. And we know very little about the design because the design report was not available. The actual site was constructed very differently than was reported in the drawings, but as-built are not available. But based on the construction records, the finally constructed liner included a 40 mil, not a 30 mil, a 40 mil single-sided textured LLDPE geomembrane. It also included an underlying geotextile, a non-woven geotextile 10 ounces per square yard as protection. Now, what about the subgrade? Well, regulations required a 6-inch clay compacted clay subgrade. There is not much documentation on how it was done, but this is reportedly what the earthen components underlying the liner were. So there was, from the bottom up, the underlying substrate was a strong sandstone. The sandstone was excavated. So actually they were reportedly blasted in order to create the excavation of what ended up being this pond. Now, the clay subgrade that the regulations required it to be 6 inches thick were placed over this series of shots of blasted sandstone, and the clay subgrade was reportedly 6 inches thick on the side slopes and 4 inches thick on the base of the pond. Now, in order to supplement these 4 inches into the required 6 inches, 2 additional inches of a material identified as wash screenings, which were reportedly some some coarse grain material, but not necessarily rocks, were adopted to cover the base, not the side slope, but the base of the pond liner. The classification of this material is not clearly reported. Now, what about, it was so different, what about the construction quality control? My assessment is that quality control was particularly deficient, and if one lesson is going to be learned after this case is that not only the operations, but also certainly the design and the original construction of the facilities need to be properly documented. In particular, when it comes to the subgrade, no tests were conducted or at least reported, despite there were regulatory requirements of certain type of subgrade material, but the actual particle size distribution was not reported. No documentation is available on the actual, there were required construction procedures for compaction of the subgrade material, but they were not available. And no as-builts, as I have mentioned, had been produced, even though the as-constructed liner was clearly very different than what was designed. When it comes to the quality control of the actual liner, this is it. So 3 handwritten air test logs that all they report is just that they passed and the date. And there were at the anchor areas, there were some samples that were taken for geomembrane trials, some peel and shear tests, but essentially in front of you is the entire documentation, the documentation of the entire quality control program at the site. Very different than as designed, very little documentation. Potentially, we have here a case of a problem in which at the very least, and I'm going to concentrate particularly on the subgrade characteristics were not clearly reported. So I talked to you about the timeline, the design. Let me get you into the liquid treatment operations. So this is what took place in April 2012. And what you see here, and this is handwritten because this is from testimony, and the idea is, again, here we have again the pond. This patch in here is actually the location where geomembrane samples had been taken, so a temporary patch was placed to protect that area. And the idea is that this is the northeast corner of the facility. This is where the water treatment, liquid treatment operations were based. And we're going to be talking about 4 different lines, 4 different hoses, 2 pumps, 2 pump sets for each hose, 1 pump for each hose, but 2 sets. Why 2 sets? One was a suction hose that was collecting the liquid, then this went to the treatment facility on site, portable, and then was returned back as in the discharges hoses. So you're going to be hearing me talking about the suction hoses and the discharge hoses. The suction hoses are indicated here, suction, 2 of them. Set 1, this is the suction hose set for set 1. and they were installed at the beginning of the water treatment operations, and they were never moved. They were comparatively short, reportedly one of the segments of the hoses into the water. Now, the end, then there was a second, this is the second suction hose for the second operation coming from the same location, around the same location. The two pumps, all the pumps were located at the northeast. Now, in complementing the suction hoses was taking the liquid for treatment, water was treated, and then it was disposed back into what it was. There was another line starting from here and ending at this location, X. This is the end, or the reported end, of the discharge hose. The operations require that the suction and the discharge are very far away, so that's why the suction hoses were near the northeast corner, and here at the very end along the north side was this discharge hose of the system number 1, and here's the second pump, second suction hose, and the discharge hose of the second suction was reportedly, and again this is based on testimony, around this location. Okay, so here we have a view of the water treatment operations at the time of the treatment. You're gonna see all the hoses that get into the pond are green hoses. These are HDPM hoses. These are comparatively lighter than other type of hoses that were not used. And they were not used on the pond area, but they were used on land. These are comparatively heavier and more flexible hoses used essentially on land. And here we have a collection of the set 1 set of hoses, suction and discharge. Suction gets water, discharge retrieves back, and this is the second suction hose, and this is going to end up being the second discharge hose. Collects and retrieves after treatment the 2 lines. All right, so this is a view of the peak of the site during operation. This is the suction hose for the system number 1. This is the end. This floater marks the end of the suction hose number 1. This is the discharge hose, and we do not see the end. The suction hose was supposed to be towards the surface or floating without touching the bottom of the liner. It was not moved during operations. This is the discharge hose that supposedly ended up at the end of the north face of the liner. And this, as I'm going to show you, there will be some operations in which the discharge hoses were resting at the bottom of the pond. Unlike the suction hoses, there were operations to move these rigid hoses, but radially, in order to capture to discharge at different locations during the operations. This was over the course of kind of, give or take, 10 days, 2 weeks. Reportedly, the hoses were not dragged in order to move the locations, but air was pumped into the discharge hoses. The hoses would then float, the hoses would be relocated, and then air pumping would stop, and the hoses could descend again to a new position. What you see here is a suction hose, the suction hose for the second line. Here it kind of starts seeing the edge of the floater for the suction hose, and not seen in this picture to the left of this picture is the discharge hose number 2. So this is a very important picture, one of the few that were really showing the layout during operations. I'm going to zoom in into this picture because you see that these buoys were tied to, in this case, to the poles in the fences. And I'm going to point to the pole. Actually, I am the one that numbered these poles. You're seeing here that this buoy, this floater was tied to, within an angle, was tied to pole number 17 on the north face of the facility. Okay, Now, what about the rocks? Well, after the cleaning operations and water pressure cleaning of this, the membrane, samples were collected, and you're going to see these irregular patches that were collected. They were still available, but they were collected before removing the entire geomembrane set, and they were preserved. You'll see here panels that eventually will be cut, but before cutting these panels, some irregular cuts had been made. And here you can see the exposed rocks that were identified when removing the liner and the underlying geotextile. Here you see, so the subgrade material was placed over the shots of the blasted sandstone. The classification of the subgrade material had not been reported. We did have access to some of the buckets that were collected in this area, but the site was not available at the time that we were conducting this investigation. The geomembranes were, but not the site. And the position testimony, even though this is contested, indicates that even the clay subgrade actually had some 50% or so of the materials that had been blasted before during early operations. Okay, but then the panels were cut. Here we see the cutting after the geomembrane and the geotextile on what were panels were. This was divided into 18 panels, A, B, C, D, E, F on the side slope, and this is what you see are the panels after cutting panels E and F, and you see a significant number of rocks. With team, we have a disagreement on how these rocks were exposed. I'm not going to get into that, but essentially, team contends that this was a product of erosion after having water having been access. The subgrade got access because a defect occurs first. I contend that erosion underlying geomembrane, that's not how water moves. Essentially, if a defect occurs, water in the underlying unsaturated subgrade, the subgrade will suck in the water, and after having sucked in enough water, then it's wet, and after it's wet, then water continues to move at the interface. This is the famous wetted radius that will take place. But at the time that this wetted radius is expanding, essentially the pressure had been equalized. So the pressure under the liner is pretty much the same pressure as above the liner. So the mechanism of flow occurs, but it's not by no means or what I consider that is not a turbulent type of flow that could cause erosion. And what may have happened, however, is that the subgrade may have been poorly compacted, and after wetting, there is a phenomenon that is called hydrocompaction, in which there is self-weight that causes now on a wet subgrade and facilitates the exposure of the rocks. But in any case, these are the rocks obtained at the location of the location where these panels were extracted. If you wash these rocks, they are very sharp. They are very sharp and clearly resemble what may have been shards or after blasting operations. Indeed, here you see an original rock washed as retrieved from the site, and this is a fresh cut that we conducted in order to compare the view of a clean cut and of the actual retrieved soils. And I'm going to show you two pictures here. One of these two is a clean cut conducted in the lab, and the other is a washed, exposed rock as it was retrieved from the site, and really cannot tell the difference, indicating so the material was particularly angular, and many of these rocks were in direct contact with the geotextile and the geomembrane. So this was a complementary background that I wanted to provide. Let me now get you into what are the causes, or this part 2 of the view of the causes of these defects, these geomembrane defects. So important questions that I'm going to try to answer were the defects induced by upward protruding objects or from downward protruding objects or impact objects? Do the location of the geotextile defects match those of the geomembrane defects, the geotextiles and the geomembrane? If there is a matching between the defects of the two, this is an important indication that the defects may have caused by underlying objects. Were the cam locks in the hoses protected during water treatment operations? Did the fluid pressures, what was the role of the fluid pressures and how this affected the geomembrane defects? Now, what about the distribution, the layout of the hoses and the location of the highly concentrated defects in the geomembrane? How do they really match or they mismatch? And finally, what we were trying, these are very interesting shapes, and I'm going to show you some more details on how these defects look like, but can we reproduce those defects in the lab? And I'm going to show you some findings that we got from that effort. All right, so inventory of defects, a very detailed. We had these 18 panels, A, B, C, D, R, 18 panels on the area of significant defects, and every single hole was pictured and was cataloged. We see here the total of holes, a total of defects, not of holes, of defects. 479 defects in these 18 panels. Initially, they had been reported to be around 200, but when we conducted this very detailed review, we identified shy of 500 defects. Now, not all of them. We tried to be very comprehensive, and we may have missed some, but if it was a hole, we cataloged it. And these are the holes that were identified in panel A, B, C, D, R, adding up to somewhere on the order of 440 holes. There were other defects in the geomembranes that we classified as imprints. By no means this is a comprehensive list of the imprints. These were typically, we identified them when sometimes the holes, next to a hole, there were a number of imprints. We didn't count those as separate imprints. We counted imprints when they were kind of isolated from other holes. And we identified, and again, we believe that this is a comprehensive listing of all the holes. This is reportedly a non-comprehensive, but hopefully as representative as possible, a number of imprints, that defects that had not reached the category of a hole, that did not go across the geomembrane. Now, what about the orientation of the flaps? Or these defects had flaps? Well, we classified were particularly, or the orientation of the defects. So 472, the great majority, the vast majority of the defects had an upward flap. That doesn't necessarily mean that the only way to create an upward flat is from an underlying object. Potentially an upward flat could be caused by a overlying object, but 472 out of the 479, that's too systematic. Not having downward holes, flaps or defects was particularly striking. There were downward, and we didn't find any downward flap, but we did find some downward imprints, and we identified 5 of them. And we also identified 2 others, such as defects in some of the seams. Okay, so this is a very comprehensive inventory, and we rely heavily on it. So let me show you a little bit on how this inventory was conducted. So I told you that we have 18 panels. This is panel number A. This was on the side slope of the facility, on the north side, but on the side slope of the facility on the northern liner. And here we have five defects on what we call geomembrane panel A1. Why A1? Because really the panel A had been chopped off on pieces that we had available, but had been cutted earlier. Geomembranes reportedly cutted at the locations where there was a high concentration of defects. So this is A1, then we have A2 and A3. Here is what was considered geomembrane A2. Again, in this case, we have a number of additional holes. And in this case, the membrane, in most cases, but not in all, we reported the defects, not only taking pictures from the top, and then we had pictures of each close-ups of each individual hole. And here is the top of the geomembrane was a textured side, the bottom of the geomembrane was an smooth side, and here we have the same defects from the top and the bottom. And this is geomembrane portion A1, A2, this is A3. This is A3, this is panel, what belongs to panel A, this is what belongs to panel B, and here are additional holes identified in panel B. So now we have the holes that were cataloged for geomembrane subpanels A1, A2, and A3, and we end up forming a composite view of the entire panel A. Here it is. So these are the 5 holes in panel A1, subpanel A1, A2, and A3. In some cases, and panel A was one of them, this was done in the field. This picturing was done in the field, and we can see that we collected additional samples, not only of the geomembrane, but also of the underlying geotextile, in this case, the southern portion of panel A. Same goes for, in this case, is another panel, panel D. I'm showing the panels that from which samples of the geotextiles and geomembranes were collected and taken to the lab for additional testing. And this is a cutting of the geomembrane that had been done on the underlying geotextile from geomembrane panel D and geotextile panel D. And this is a third panel from which samples were collected. These were the A and D were on the side slopes, D was on the base, and here we had a view of the defects in panel D. Why it was done this way? The coordinates were identified within each panel, local coordinates for the different components, and eventually overall inventory of the geomembrane defects was collected. Here are the 430 something holes and the imprints that had been identified. Panels A to F were in the side slope. This is the toe of the side slope. These panels G, L to R are on the base of the site. So this was the outcome of that evaluation, but in addition, this was accompanied by a detailed picture of each one of the defects. So the inventory included a total of 479 defects. 438 of those were holes. 41 of them identified in this picture are imprints. 472 of them have upward orientation. 5 have a downward orientation, and no identified in this area. And again, there were other areas other than these 18 panels, but in these panels, there were no identified scratchers or linear features in this collection on this particular location of the site. Let me walk you, and I try to enlarge the pictures just to give you a sense on how these defects, what was, because one thing is defects, the other is what are the typical defects. And here we have the entire inventory of defects. So I'm gonna try to tell you what the most typical defect was. This was probably the most typical one of all. This is on panel A. And here we have what we call 2 defects. This is a hole, and this is an imprint. Here you have a clearly upward oriented flap. We rarely have seen these flaps being cut, so we may have missed some, but to the best of my understanding, the flaps were all in there. But what is interesting is that there is this defect, but it didn't make it into a hole. But maybe when we have an imprint, we have more here there could be arguments, well, was this flap caused from an underlying object or from an object going from the bottom, from the top down, perhaps in a swing mode. But when it's an imprint, it's clearly from the bottom up. So this is a forensic tool that we use to identify when these defects were from the bottom up. So this is the top, the textured side, and this is the bottom. This is the bottom, the smooth side. This is the same defect as the one presented in here, and this is the same imprint as this one collected in here. And in our opinion, these were clearly caused by objects protruding from the bottom up. Let me just show you, this is the same defect that I showed you before, but this I showed you in the context of the other defects, and typically we had families of defects. But the reason that I'm showing you this is to call your attention to the orientation of the flaps. So there was no particular, some of them are oriented north, some of them east, some of them south, some of them west. So here you have a collection of, I think that here we have 7 defects and flaps, all of them oriented in no preferential orientation of the defects, which may have been potentially the cause had a very systematic hose, and a linked hose from the top being causing these defects. This is another view just to show you that this is one type of what were called representative holes, and sometimes pictures are hard to say, are these upward or downward, so sometimes we took pictures in an angle just to show these were all upward oriented flaps. And here we have another one. I'm going to go quickly now in this, but we can, each one of these holes, this is a hole and an imprint. Each one of them has a story behind it. This is another one, and I'm going to accelerate so that we can leave time for questions. This is an imprint that was collected from the bottom up. This is an imprint that was one of the few linear features. All the features that we found were imprints, no holes, going from the top down. And we found no scratches other than scratches that, for example, this was caused after the painting, so clearly post liquid treatment. I'm gonna skip these summaries that I have just presented in order to expedite this presentation, and let me walk you through the geotextiles. Geotextile is much harder. We try to map the geotextile holes on site, and it's really hard. For example, we match these geotextile defects in here, but how do I prove that these were real defects? We put some rocks in here that align with the defects. So what we really did is to evaluate a sampling of the geotextile defects on the samples that were taken to the lab, and we clearly mapped the geomembrane defects to the underlying geotextile defects. Here is an example, another example, the geotextile, even we see the defects, but it's hard to document. We found a way of documenting them that involve placing them in a dark room with an underlying lighting, and here you see more clearly defined the geotextile defects. Let me walk you very quickly through the cam locks. These are the view of the cam locks. These are the inventory of all the green cam locks that were 25 of them. Most of them were 20 feet long, even though some of them may have been up to 26 feet. And this is the full inventory of them. They're rigid. One way of measuring the rigidity of the hoses is through their bending radius. And here you have, are the most rigid, among the most rigid in the market. They were reportedly taped, even though this is something that has been under dispute. And not only that, but this is a picture taken during the watering. But in addition, you could argue that these sediments also existed at the time of the water treatment. So the sediments could have been a second protection layer. And you could argue that buoyancy plays on favor, and this is an artistic rendering of what Archimedes' principle may do to a submerged camlock, and may play a role in minimizing the impact of a submerged hose compared to portions of this hose that were in air. Now, interestingly, the hoses portions that were in air did not have reported defects, but the defects were identified underwater. Supposedly, in principle, and I'm not going to get into the discussion at this point, but supposedly this sustained pressure, the sustained pressure causes a loading of a protruding rock that may lead to a rupture, potentially may lead to a rupture at a load or a pressure that is much lower than the one that you could obtain with a rapid type of loading. But the buoyancy of the camlocks was evaluated and was documented in the lab. Ultimately, the weight of the camlocks when filled with water was 1/3 of its original in-air weight. And this is probably an important aspect that I want to walk you through, which is at the end, where were the hoses in relation to the defects? This is a Google Earth map superimposed with a drawing at the facility. This is the base, the toe of the side slopes. This is the reported location of the water line. And here is the edge of the crest of the side slopes. Okay, so where were the hoses? The defects. Here is the location of the defects. These are the 18 panels that were retrieved and where the great majority of the defects had been located. These are the suction hoses. These are the suction hoses. This is pole number 17 that I had shown you before. This is the rope tying the hose. This hose is viewed in a picture. This is 20 feet long, may have been 26 feet long at the most. But this is one of the segments of the hose. Didn't make it. The suction hoses didn't make it to the location of the defects. The same goes with the second suction hose. Suction hose didn't make it to the potential location of the defects. Let me clean this up and now add the discharge hoses. This is what discharge hose number 1. This is the one hose that had not the end, but some of the connecting camlocks potentially acting on the area of the defects. However, the range of movement of this discharge hose was a radial one. So consequently, the holes, the defects could hardly been explained by being caused maybe by one or maybe two of the different camlocks. And this is the discharge holes number 2. So there are two important questions. One is, were these diabolic camlocks cause the defects at this location? But the other important question is, why not this camlock? And why not this camlock? And why not this portion of the camlocks that were exposed in air, where the potential problems associated with the hoses is significantly more relevant? So the layout doesn't play when we want to blame these different hoses to the particular location of the defects. And here is a close-up superimposed in this case, and here I'm chopping this off just to show the range of movement of one of the camlocks, superimposed with the defects. Potentially impossible is not impossible, but I would say that it's much more likely that other hoses in other locations in air could have caused more damage than the ones in here. I'm not going to walk you through this because I'm running out of time, but we conducted tests that essentially this was a quest for finding the fingerprint of the defects that were identified. And another important aspect is that even in damaged geotextiles in the lab, finding the defects after the fact is even hard. But this is a 3D imaging of a actual defect in the sample collected from the field. We tried to reproduce this defect in the lab. This is an actual rock retrieved from the field. And this is an impact causing, in the geomembrane, kind of causing what we would, a defect that would resemble a defect identified in the field. Here's the 3D scanning of that one defect caused in the lab. But what about the cam logs? Can the cam logs do this, cause a defect? Here's a drop of the cam log into the geomembrane. They cause a defect, they cause a marking, but this by no means is the typical markings or a fingerprint of the defects that were caused in the field. This is on the geomembrane, this is on the geotextile. What about and this is the 3D version of the 3D scanning of the defects that were caused by the cam locks. What about the swing in motion? We really tried hard. We really tried hard, but the type of defects that we would have are linear defects, not necessarily, and this was in air. This was in air. So swinging, we couldn't reproduce the defects that were identified in the field. Finally, as a final verdict on the fingerprint, and then again, there's probably different ways of doing this, but this is an attempt to identify what could have caused, reproducing in the lab, what could have caused a defect. This is from the field. This is from a rock impacting from the bottom up, and this is from a cam lock acting from the top down. I'm going to leave it up to you which ones of these match the best. And this is a different rendering of the same. This is the lab from the bottom up. This is the field, the actual one, and this is the cam lock from the top down in the lab. So, conclusions. Following the compilation of a comprehensive compilation of defects, we concluded that the preponderant direction of the defects from the top was downward. We concluded that the geotextiles and the geomembrane defects did match. No information was available that can refute the fact that the cam locks were protected, but even if they were not protected, there were other palliatives to the potential impact, including buoyancy, including the presence of sediments. An evaluation of the geometric layout. Out of the 4 hoses, 3 of them didn't cause any damage. 1 of them could have caused damage, but it is an important aspect in this puzzle. And finally, the fingerprint of the defects that we found in the field could be reproduced in the lab using rods and could not be reproduced in the lab using cam locks. Recommendations. And I'm done. These are recommendations that Tim presented, and I fully endorse them. These are recommendations regarding how to avoid the potential problems associated with and this is a valid concern, the problems associated with hoses and operations in oil and gas operations, ponds. These I could say is for both parts on 1 and 2. Tim and I agree that whenever you're going to do operations of removals, shovels, and pressure washing should be out. And from this part 3, this is essentially saying that the design of line ponds used for oil and gas should not be overlooked. Quality control and design guidelines are in place, and design material specification and quality control for impoundments serving the oil and gas industry should not be any less stringent than those used for storing other hazardous liquids. And with that, thank you, everyone. I really want your questions, and I know that we are short of time, but I'm going to ask Tim to take it over from here.
Okay, great, Jorge. Let me see if I can get through a few of these questions. We have a number, and again, we'll do the ones we can't get through in a podcast. Number 1, did they plug the discharge hoses before pressurizing them with air in order to move them?
Can you repeat that, Tim? What did they do?
Did the operator plug the discharge hoses before pressurizing them with air in order to move them?
It was not reported that that was the case, but it was, as I understand it, it was pumped, air was pumped, and that was enough to cause the rising of the entire hose. Remember
Right.
that in when submerged, the weight of these hoses was a third or so, including the steel, of what it would be in air. So air was pumped, and that was reportedly how it was raised.
Right, but if it wasn't plugged, air was just going out the other end.
I agree. Yeah,
Yeah.
that's it.
Okay. All right. Were any of the holes brittle stress cracks, or were they all ductile tears?
I would characterizing as brittle, and I would say that this is throughout the entire spectrum of the defects that were identified.
Okay. Why was the textured side of the LLDPE geomembrane not placed on the geotextile? In other words, why wasn't the texturing down instead of up to give some interface, higher interface strength?
Yeah, I do not have much information about the rationale for the design. I suspect that this is to facilitate operations on top of the geomembrane. So, for example, walking or cleaning, but that's my based on my reading, it was not reported, or at least I do not recall this being reported. But that's a very good question.
Okay, next. Would the jetting of liquids exiting the discharge hose on parallel to the bottom of the pond cause an uplift of the geomembrane and or the hose?
I don't see that happening. So if you have a hole, and we have done tests at much higher levels of pressure. Essentially, what happens first is water infiltrates, and after water infiltrates, maybe reaches a point. This is unsaturated flow. Reaches a point in which the capacity for the water to suck this moisture is exhausted because the hydraulic conductivity, the gradients drop. But at that point, the pressure of water at the interface, at the location of the hole, is the same as the pressure from the top. So there are mechanisms of flow along the interface or into the soil, but not pushing. There's no pressure from the bottom up to cause that. If anything, the pressure comes from the top down. Eventually it equalizes. And that's when the other mechanisms of flow, let's say radial flow, may occur. But there's no source for pulling water the membrane up, in my opinion.
Okay. What if there was no defect in the geomembrane? I think that's what the question's asking. So there's no defect, the hose is just on top and it's exiting water from it. Could that cause uplift as the water's shooting across the top of the geomembrane?
Oh, from the top down.
Yeah.
I didn't think about it. My first reaction would be that if anything, this could raise the hose rather than uplift the geomembrane. But that's a scenario that I don't think so. But at this point, I do not have any calculations or to back that up. My reaction would be that the hose may end up being a lift or moved, but not necessarily the membrane.
Okay. The geomembrane used was LLDPE and 40 mil thick. There's a question there. Okay. Next one. The recommended geotextile sandbags, should they be placed at the bottom of the geomembrane layer or at top and bottom? So those are I think they should just be placed on top of the geomembrane and then the hose sits on top of them.
Correct. Yeah, that's a recommendation. That is not necessarily the practice. To the best of my understanding, Tim, you may comment on that because this is a recommendation that you had, but I think that this is a recommendation for future use. I have not seen it being implemented so far.
Right.
Yeah, or reported. Yeah.
Was there any indication of the time the geomembrane was exposed to UV light, potentially exacerbating the degradation?
That's a good question. Reportedly, this was underwater. There was a drawdown to the defects. This happened around June, but soon after this, the area was covered. What you see is a tarp, a geomembrane tarp. So it was not directly exposed for long periods of time to UV, because it was covered. I think that the rationale was to protect it from infiltration from rain, but at the same time, it protected it from sunlight.
Okay, great, everybody. Thank you. There are a number of other questions. Please send additional questions through the post-webinar survey, and we will answer them in a follow-up podcast. The questions are still coming in. So Jorge, can you go to the next slide?
Yes.
Okay, so next should be contact information. If you'd like to contact me or Jorge about the project, there's our email addresses, and this is in the PDF. Next slide. Our next webinar is May 18th, 2023 at noon Central Time, and JP Giroux will present his Kerner lecture on May 18th titled Zero Leak at Installation to Zero Leakage in Service Life. Really great presentation. I saw it during Geosynthetics 2023 in Kansas City. Next slide.
Awesome presentation, and very, very, in many aspects, connected to this discussion that we have had.
Exactly, very related. And here's our website. Check out our website. Next slide. And I think that's it. That's it. Okay, everybody, thanks for joining, and please send in your additional questions, and Jorge and I will answer them in a follow-up podcast. Thanks for attending, and I hope
Thank you, everyone. Thank you very much for your attendance. Thank you, team, for putting this together.
Great job, Jorge. Thank you.
Very good. Thank you. Bye-bye.
Bye.